Hello everyone, welcome back to our generator protection series. On this video we will talk about the generator protection testing using the Test Universe Power Module, and we will explore how the advanced module test module can be effectively used to perform generator protection testing, and we will walk through the testing of generator protective function including the overcurrent, under excitation and reverse power protection. We will demonstrate how to use power view, power shots and power ramps to verify both operation and trip times, ensuring that each relay responds correctly under simulated fault condition. So let's get started and see how the advanced power module can be used to test and verify this protection in the real world setup. So the goal of this video is to help you to understand both the functionality and the practical operation of the advanced power test module, focusing on key generators protection function. By the end of this training, you will see and you will have a clear understanding of how to set up and execute the test of different generator protection schemes using the Test Universe Power Module. And throughout this video, we will carry out some practical exercises based on the selected protection function, including overcurrent protection non-directional designated as NC50, reverse power protection known as NC32R, and under excitation protection with NC code 40. So each of these functions play an important role in ensuring generator stability and reliability. Here we can see the generator capability curve plotted in the PQ plane, where the horizontal axis represents the active power and the vertical axis represents the reactive power. This curve defines the operating limits of the generator under different load and excitation conditions. However, for protection testing purposes, especially when dealing with a function like under excitation or loss of field, it's often necessary to represent this curve in the RX plane. This conversion from PQ to RX allows to express the generator's operating points in the terms of apparent impedances as seen by the protection relay, and by doing this we can simulate a realistic operating conditions and verify how the relay responds to different parts of the capability curve, ensuring accurate and reliable protection behavior. So in this section we will look at the system setting under the test object of the power module, as you can see in our configuration, and the reference here for all the calculation is that it's based on the generator rated apparent power denoted as SRG, and this ensures that all derived values remain consistent with the generator actual operating parameters. Also, the values entered are taken directly from the relay manual to maintain accuracy within the relay protection characteristics. At this stage, also no voltage protection function are enabled, as we are focusing on power-based functions. It's important to note that we are using a separate zone configuration which can be reviewed under zone setting, especially the overcurrent protection zones. And additionally, all parameters visualized and displayed in this setup are shown in primary values, providing a direct and realistic reference for the testing. So you can see here the system parameters, the CT start point is grounded towards the line, and also here is the reference of the reactive power in the nominal device power, which equal to 31 megavolt ampere, and here is the relative and the absolute tolerance for the time and for the apparent power, as you can see, and also for the angle, and here is a voltage threshold which is disabled in our case, and here is the overcurrent threshold also. We will display all of these values in primary units just to give you a real sense of the parameter setting. So under the zone setting tab here, we can see the generator capability diagram as referred as the operating area, and the diagram also is provided for only reference, and it helps you to visualize the generator permissible operating limits in terms of active and reactive power. Also, it's not directly used for protection calculation because it serves as a useful tool to understand the relationship between the relay settings and the generator actual capability curve. So we have different zones as you can see, and we will walk through all of these zone settings. So in the zone setting and the operating area, as you can see, here is our view of the operating area, and here is the necessary parameters for defining the protection zones can be read directly from the generator capability diagram, and this makes it much easier to align the protection testing and the protection setting with the actual operating characteristic of the generator. So for example, here we have the element number 1 and element number 2, which shown as line Cartesian. So here is element number 1 in red, element number 2 in yellow, and here is the intersection point in the power Q plane, in the PQ plane. So as you can see here is line number 1, it intersects with minus 12.7 megavar, and line number 2 intersects with minus 14.88 megavar, and here is the angles, and both of them are expressed as a line Cartesian. Now we will talk about the element number 3 in blue, as you can see. So in the PQ plane also the P will equal to 0 and the Q here will equal to 0 var, and the radius here is 31 megavolt ampere, and here is the start and the end angle for draw this element number 3 as our Cartesian. Here is the element number 4, which is expressed here as arc Cartesian as well, and we can calculate the 0 point on the generator capability diagram. So this formula used in V phase to earth of the generator in square divided by the XD. So the phase to earth is the rated phase to earth voltage of the generator, and XD here is the direct axis synchronous reactance. So substituting this per unit values, we get 1 per unit divided by 2.08 per unit, which means 0.48 in per unit values, and this means that the corresponding 0 point occurs at 0.48 of the generator rated apparent power, considering a generator rating of 31 megavolt ampere at this point. So we multiply 0.48, resulting in 14.88 megavolt ampere, and this value defines the location of the 0 point on the capability curve. Now in the zone setting, which is the P reverse configuration, we define the pickup value of the reverse power function, and this pickup setting is specified as minus 1.5% of the generator rated active power, PRG. So using the generator rated power of 31 megawatt, the calculation is straightforward. So P equal to minus 1.5% of 31 megawatt divided by 100, which means minus 465 kilowatt. And this means that when the generator begins to absorb approximately 465 kilowatts of the power, instead of delivering it, the reverse power protection will detect this condition and initiate a trip or alarm depending on the relay configuration. So this function is crucial for preventing motoring operation, which can cause overheating and mechanical stress on the turbine and the prime mover. So this line can be expressed as a line Cartesian, as you can see, and the power equal to minus 465 kilowatt, the Q equal to 0, and the angle here is 90, which is the red line we can see on our graph. So now we will talk about the zone setting of the thermal overload configuration, and the pickup value is set to 1.1 times the generator rated current, IRG. And this means the protection will begin to respond when the generator current exceeds 110% of its nominal value, indicating a thermal overload condition. So this element is configured as an offset circle, as you can see from here, and with angle 0 degree as shown. So using the apparent power formula, S equal to root mean square of 3 multiplied by voltage multiplied by 1.1 of the rated current, we obtain the apparent power of 34.05 megavolt ampere, and this value represents the point at which the generator starts to experience excessive heating due to overcurrent. So setting the pickup slightly above the rated current allows the generator to handle short duration overloads without tripping unnecessarily, while still ensuring protection against sustained thermal stress that could damage the stator windings and insulation. Now we will talk about setting zone of the overcurrent protection configuration, and the pickup value here is set to 1.3 times the generator rated current, IRG, and this element is configured as an offset circle, as we explained before, with the angle equal to 0, and the corresponding here to the operating threshold of the overcurrent protection OVC function by applying the apparent power formula S equal to root mean square of 3 multiplied by voltage multiplied by 1.3 of the rated current. So we obtain an apparent power of 40.3 megavolt ampere. This means that the overcurrent protection will activate when the generator output reaches approximately 130% of its nominal current rating, and the purpose of this setting is to protect the generator against excessive current caused by the short circuit or abnormal loading condition, while still allowing for a brief current surges during the transient or starting events, and this ensures a reliable operation without unnecessary tripping under normal system fluctuation. So in the zone setting of the under excitation characteristic 1 and 2, as you can see from our screen, we define the main parameters of the under excitation protection zone. So in this case, the protection setting is 0.43 per unit at angle of 68 degree, as you can see from the protection setting, with a trip time of 3 seconds. So using the generator apparent power of rating, so the SRG equal to 31 megavolt ampere, so we can calculate the corresponding reactive power as minus 0.43 multiplied by the apparent power SRG, which equal to minus 13.33 megavar, and this value represents the reactive power limit below which the generator enters an under excitation condition, posing a risk of loss of synchronism or overheating in the end region of the stator, and the 3-second time delay here to ensure that the short-term fluctuation in excitation does not cause unnecessary tripping, while still providing a timely protection against sustained under excitation operation. So the protection parameters are defined also with a setting of 0.35, which is characteristic number 2, as a per unit value with angle of 90 degree, as you can see, and the trip time also is 3 seconds. So using the rated power or rated apparent power of the generator, which is 31 megavolt ampere, we can calculate the corresponding reactive power at 0.35 multiplied by the apparent power, which equal to minus 10.85 mega var, and this point represents a deeper under excitation condition compared to the previous zone. And when the generator operates in this region, the excitation is significantly reduced and increasing the risk of instability and excessive heating in the rotor. Now we'll talk about the protection parameters also of the number 3, and you can see here now it's defined with a setting of 0.7 per unit and with an angle directionality from 20 degree up to minus 20 degree from here, from the line 1 and from the line 2, and here is a blue zone which represents this zone number 3 for the under excitation, and using the generator rated apparent power, which is 31 megavolt ampere, so the corresponding reactive power in this case will equal to 0.7 multiplied by 31 megavolt ampere, which equal to minus 21.7 mega var in both line, and this zone represents a severe under excitation condition where the generator operates deep within the unstable or transient regions, and at this point the excitation level is critically low and the risk of pool slipping or loss of synchronism becomes very high, and because of this the trip time is set much shorter, only half second, as you can see from the protection setting here, to ensure a fast disconnection of the generator before mechanical or thermal damage can occur. So this slide provides a summary of the test object and generator protection setting zones used throughout our slides, and the symbols shown here corresponds to a different characteristic displayed on the RX diagram. So the symbols here 1 and 2 represents the generator capability diagram and thermal overload curve, as you can see in red color, which are shown only for reference, and this help you to visualize the generator operating limits. On the other hand, for the symbol 3 and 4 indicates the trip characteristic of the under excitation protection related to the static stability, and this zones protects the generator against low excitation conditions that could lead to instability over a sustained period. Now the zone number 5 corresponds to the under excitation protection for transient stability, which operates faster to detect a sudden loss of excitation. The characteristic number 6 here represents the reverse power detection or the reverse power protection characteristic designed to detect a power flow reversal when the generator starts to motor instead of generating. And last but not least, the characteristic number 7 marks the overcurrent protection characteristic corresponding to the definite time stage, which is the DMT, and together this curves provide a complete overview of all key protection functions configured and tested in the generator protection setup. So here we will talk about the hardware configuration. So for the testing, we first need to adjust the hardware configuration, and in our particular example here, all protective functions are connected to the start point CTs, which means side 2, and we need also 3 phase of the voltage. And to simplify the testing process, we only need the start and the trip triggers, and this setup ensures that the protective relay responds correctly to the simulated fault conditions. So in this part also of the OCC file procedure, we focus on verifying the general wiring setup, which is the part number 1 in yellow. So this section of the OCC file is used to check that all the CMC connections are correctly wired, which will make troubleshooting much easier later on. And also once the wiring is confirmed, we proceed to test the protective function over current, OVC, under excitation, and reverse power protection function using the advanced power test modules in the red box. So now we will talk about the test setting, which is applicable for all tests, as you can see. So we will use a test model with a constant test voltage, and here is the V-test, which in primary value equal to 6.062 kilovolt, which means phase to earth voltage in primary equal to 10.5 kV of the rated phase-to-phase voltage of the generator, and in secondary values will equal to 100 voltage, which is the secondary rated voltage of the VT. And also we have here the maximum current also, which is 8,000 kiloampere, which means 4 of the rated current in primary values, which means 4 ampere in the secondary values. And also you can see here the pre-incident state, which is used in direct set mode for injecting 3-phase voltage and 3-phase current. Also here is the reset state. So to talk about how to test the overcurrent position, and here is the test view of the power ramp. So here is the test view in the advanced power module. So we have a power shot tab, we have a power ramp tab, and we are using now the power ramp for identifying the pickup and the drop off of the overcurrent protection. And as you can see, you can define the incident type to be 3-line. Also, you can define the ramp type to be step or to be smooth ramping, and also the ramp mode here to be used in B over Q or S and phase angle indicated by phi. And here is the start and the stop of the power ramps, but in terms of S and with different phase angles which equal to phi. You can also use the nominal frequency, which is our 50 hertz in our case. And on the delta side here, you can define this delta to be an apparent power or active power or the phase angle. So we are using now the S, which is our apparent power, because we are using the power ramps. So we will use the step size of power equal to 1 megavolt ampere and the step duration to be 1 second. And then we can define the ramp assessment, as you can see blue. Here's another example also of how to test the overcurrent protection in the power module using the power view. So for testing the overcurrent protection pickup and drop off, we can use the power ramp, and also we can define the assessment. So we can focus on the test lines here defined in the test view as shown in our previous slide, and the trigger condition here to be used with the start contact changing from 0 to 1 for measuring the megavar and the megavolt ampere. And this testing structure is similar to the ramping test module and allowing you to gradually apply power values and observe the relay response under controlled conditions. Here is another example of how to test the trip time of the overcurrent protection. So you can use the power shot in this case, and we can use test shots defined in the test view, as you can see. So we have 2 test shots which can be defined in 1 and 2. For sure, the test shots number 1, we are expecting a trip, and test shots number 2, we are not expecting any trip because it's blue and it's inside the characteristic of the overcurrent protection. So for example, here the time assessment is performed for the test shot 1 to verify the relay response. Unlike other tests, the trigger condition start here is not used by this module, as the test execution is controlled directly by the predefined test shots, and this ensures accurate measurement of the trip time for both shots. So shot number 1 will be trip, while a shot 2 no trip expected. So for testing the under excitation protection characteristic 1 and 2, we can use also the same functionality as for the overcurrent protection test using the power ramps, and also a separate assessment not necessary here because the graphical output provided by the test is sufficient to verify the correct operation. So we have 3 test shots, as you can see, or 3 power ramps to define the reach of the under excitation characteristic in our case. And for testing also the under excitation protection trip time for the characteristic number 1, characteristic number 2, we can use the same functionality also as we used in the overcurrent protection trip times, utilizing the power shot modes, as you can see. So we can define 4 number of test shots, and we can see the trip time if the test shots exceeding the characteristic, and we are expecting no trip happens if this point is below the threshold of the under excitation functions. And here is another slide also for testing the under excitation protection characteristic number 3, and we can use also the power shot module. So we can define some test shots is below the threshold and some test shots above the threshold, and we can differentiate between the expected trip times for all of these shots using the zone assessment, as you can see in blue. So this point is expected to have a trip time, and this one as well, but for the other 2 shots below the characteristic of the boundary here is expected to have no any trip. Now for testing the reverse power protection reach, we can use the power ramps, as you can see in the advanced power module. So we will use the power ramps, and we will use the step ramp in the B and Q mode, and we can define here the reach of the under excitation, the reach of the reverse power protection, and you can see also, and you can define here the assessment of the zones to be with the trip contact changing from 0 to 1 as a binary trigger condition. And here is the nominal which is expected to be measured is minus 465 kilowatt, and here is the actual value compared to the nominal value based on the accepted tolerance of plus and minus deviations, and assessed as pass in our case. Last but not least, how to test the reverse power protection also using the power shots. So simply we can place some shots above and under the reverse power characteristic, and we are expecting if it's above the threshold of the reverse power to be tripped, and if it's below the threshold to be no trip. We will look an overview about the power module in our case. So we will open now the OCC file, and I will take an overview with you how to define and how to test different functions using the advanced power module of the test universe. So you can see from here is the OCC file of using the advanced power module to test different kind of protection function. Simply first you need to do the wiring check, and you can take a snapshot also from the relay HMI to be printed out in your test result. Also you can do the same here for the advanced power module with the reverse power protection, and then you can go forward with the advanced power part for the overcurrent protection. For example, if you double click this test module. So here you can use the power ramps to test the overcurrent characteristic as we explained, and then you can see here the ramp number 1 and ramp number 2 with the start of 0 to 1 as a binary trigger condition for the Q and for the S, and here is the expected value of the megavar and the megavolt ampere as a reach in this case. Also, you can use the incident type here to be L1, L2, L3 as a three-phase. Also, you can define here the tip of the ramp to be step or to be smooth ramping. And here is the ramp module. You can select or toggle between the BQ or the S and phi. And here is the from of the first ramp, and here is the to of the first ramp. And also, you can define both of them for different values for the from and to for both ramps. And you are expecting here the reach of the Q, and here is the reach also of the S. So you can compare the actual value with the nominal value using the power ramps module. And here is the test setting which we explained already in the presentation, and here is the values in primary, and also you can toggle by using this view to toggle these values to be in secondary. So here is the V nominal in phase to earth, which is 100 volt divided by the root mean square of 3, and here is the I maximum, which is 4 times the nominal value. So you can display also in primary. Also you can display the time in seconds or in cycles. Then you can go also for the second module, which is the trip time of the overcurrent protection using the power shots. So the reach, it can be done using the power ramps, and the trip time can be done using the power shots. As we know in the advanced distance module, for example, it's just in the same way here. We can define some shots, as you can see above and below the characteristic, which is the overcurrent protection characteristic. And you see this point now is no any trip expected, but in the point number 1 here we are expecting the trip, and here is the actual tripping based on the overcurrent protection setting in the Siemens relay. Here is another example also how to test the under excitation characteristic number 1 and number 2 as power ramps or as a reach. So you can click open and then you can see the ramp 1 and ramp 2 and ramp 3. Also you can define the from and to from here for each ramp. Also you can use the L1, L2, L3 and the ramp type to be a step and the ramp mode to be B and Q. And here is no any assessment required because the graph will give you a clear view about the test result. On the other hand, also you can use the power shots to define and to test the trip time of the under excitation points. So you can define a number of test shots, as you can see, or power shots. So this test shot, which is below the under excitation characteristic here, so there is no any trip expected. On the other hand, if you see the other point here, which is above the threshold of the under excitation characteristic, so the trip time here is expected to be 150 cycle, as you can see, and you can compare the actual trip time with the nominal trip time in this case. Here is how to test also the under excitation characteristic under transient conditions. So you can use also the power shots for testing this characteristic. So for example, the test shots number 1, which is above the threshold, will be tripped, and the other test shots, which is below the threshold of the under excitation of characteristic 3, it's expected to have no trip, as you can see here from our test shots. Also you can do a lot of test shots also in third quadrant here, and then you can get the trip time of these different test shots. Another example also how to test the reach and how to test the pickup values as power values for the reverse power characteristic using the power ramps. So we can make a zoom in as you can see here. So here is the characteristic of the reverse power. We can use a power ramp, as you can see, from here up to here, and you can define here the from and to, which is the start point and the end point of the power ramp. And also we will use here a trigger condition with the trip contact to be changed from 0 to 1. Then you can measure the minus 465 kilowatt, which is available in our parameter setting of the protection relay. Then you can get the actual value of the power ramp. Last but not least, the advanced power mode also can be used for checking the reverse power trip time. So you can use the power shots as we explained before. So you can see here the two test shots. So we have one test shot which is above the threshold of the power reverse, and we are expecting a trip, and the other one which is below the threshold of the reverse power protection setting, and we are not expecting any trip to happen in this case. Thank you for watching the video, and stay tuned for the next one.